Hey there! In this video, we are going to go over what a power series is and how to find its interval of convergence and its radius of convergence. Let's go! I'm pumped! So, a power series is actually something you've seen a lot of before if you've studied Taylor series and Maclaurin series. Those are special ways of building what is known as a power series. It's essentially an infinitely long polynomial, right? And we've seen that already. We've seen that for e to the x, sine x, cosine x, ln x, and possibly other functions as well in your studies. So a power series in general is just the infinite series of some format of coefficients times x minus c, and that would be to the nth power. And it could be some form of to the nth power. Could be to the 2n, could be to anything, but I'm going to just write it as to the nth here. And so that would be a sub 0, if you just plug in n, times x minus, and it's centered wherever. It could be about x equals 0, about x equals 1, just like we did with Taylor series before. So that would be x minus c to the 0th. Well, okay, all right, that we all know simplifies down to 1, so that goes away. And then x minus c to the 1st. So you'd have a sub 1 times x minus c to the 1st plus a sub 2. Here we go, x minus c to the 2nd plus dot 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 plus, and then a sub whatever the nth term is times x minus c to the nth power, and it keeps on going on and on and on like that. So it's an infinitely long polynomial. We've seen some of those before, but we're just kind of giving it the blanket name of power series. We built power series with the Taylor polynomial and Maclaurin polynomial procedures of yore. Like of the past. Okay, all right, here we go. Anyway, we have been using partial sums of these series already, and I'm going to just kind of show you this. We did partial sums of sine, right? We had x minus x to the 3rd all over 3 factorial plus x to the 5th all over 5 factorial plus, and it goes on and on and on. So we've been doing partial sums of that and using those to do approximations. That goes on and on forever, we know. Negative 1 to the nth power times x to the 2n plus 1 all over 2n plus 1 factorial. So there's our sine series, right? That's the power series for sine. We've been calling it a Taylor series all along. As n approaches infinity, our polynomial approximation becomes a power series. We talked about that with our Taylor series. That as n approaches infinity, this thing became equal to sine of x. Okay, more on that now. So the overall question though is, over what x values does, in this particular case, sine of x converge? Because what you've got here is you've got this series for sine x, but what x values am I allowed to plug in? If I plug in 1/4, will it converge or will it diverge? So if I have x values that I plug into this and I say, hey, the approximation for sine of pi over 12 is plug in pi over 12, and we come to find out that that diverges, that approximation's no good. So we need to know the interval over which we can plug in nice x values into this, or not so nice x values, and have the confidence that that approximation will eventually approach a converging value. That is known as the interval of convergence. So the answer, again, determines the usefulness of the series. So if we get an interval of convergence that says you can plug in any x value you want, and this thing will converge, then the sine of x power series is very, very useful. So it says find the interval and radius and convergence for this. We'll go over what each of those are shortly. So that again is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot 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 all the way out to, and then we copy the nth term, go to right here, x to the 2n plus 1. I like to expand it out. 2n plus 1 factorial. Now how do we find the interval of convergence? Well, there's 2 series tests that we've used that work really nicely with these kinds of functions, but we're going to focus on one for this video. And this is the one that you should use all the time, unless you're positive that it's a geometric series. More on that in a little while. So the ratio test is the safest one to use. It involves an inequality, and it's fairly easy to use. So what we do to find the interval of convergence is we apply the ratio test. So we take the limit as n goes to infinity of the absolute value of, it's the a sub n plus first term, remember that, over the a sub nth term in a series, which would be the limit, as I'm just doing that to review, you don't have to write that on a test. I'm reviewing that. If you're having trouble remembering the ratio test, go back to chapter 9, where I go over that in great detail. So the limit as n goes to infinity of, the n plus first term would be plugging in n plus 1 everywhere into this. So it'd be negative 1 to the n plus 1. X to the n plus 1 would be, careful here, That'd be 2 times, I'll put this here, n plus 1 plus 1. That's 2n plus 2 plus 1 is 2n plus 3. All right, that's where I get that from. All over, and this is going to be the same value of that, 2n plus 3 factorial. So there's your n plus first term. You're going to multiply that by the reciprocal. It's the same as dividing by the nth term, which is just multiplying by the reciprocal of this. So it'd be 2n plus 1 factorial all over negative 1 to the n times x to the 2n plus 1. So that's it. It's the ratio test. You might be like, yeah, but we got x's. What do? You're forcing this thing to converge, right? You want this to converge. It will only converge if and only if that limit is less than 1. So we're going to solve for x that will give us values so that this is less than 1. And that would be the interval over which this series converges. That's it. That would be the interval of convergence. So we're going to solve this out. A little bit of simplifying here. The negative ones, they don't really matter. So they're going to drop out. We're going to get the limit as n goes to infinity of, you've got the n terms here. This is 2n plus 1 factorial. This is 2n plus 3 times 2n plus 2 times 2n plus 1 factorial, right? Subtracting each one by 1 as we go to the next one. Those divide out. Now, why is that important? Well, that leaves us with a nice limit to take. We've got x to the 2n plus 3 over x to the 2n plus 1. Now, you have 2 more x's in the numerator than the denominator, so that leaves me with the absolute value of x squared, and I'm going to take the n values to the outside. So it's going to be 2n plus 3 times 2n plus 2. And I'm going to maybe rewrite this a little bit neater. Where I'm getting that from and why I can take it outside the absolute value is they're n's. They're going to be positive, so that's outside the absolute value, times the x squared that's left when you divide this by that. Again, 2 more x's in the denominator. That's going to be less than 1. Now, before we figure out the x values that will make that less than 1, what's the limit as n goes to infinity of this? Now keep in mind the limit only applies to the n terms, not to x. We're not taking the limit as x goes to infinity. So the limit as n goes to infinity of this, well, that's 1 over infinity. That goes to 0. And now x, you might be like, yeah, but what if x goes to infinity? It's not going there. X is a finite value that we are trying to figure out what finite values can we plug into that. Well, any of them, because this would equal to 0. Any finite number times 0 is 0, which is always less than 1, which means it doesn't matter what x value you plug into this series, it's going to converge. So therefore, the interval of convergence, I'm going to abbreviate it as IOC, I wouldn't do that on a test though, is all real numbers, negative infinity to infinity. So what's the radius of convergence? Well, the radius is always half the distance between these things, right? Just like, think of this almost as like your diameter of a circle. So you take half the difference between those, which again, and I'm going to call it the radius of convergence, would be equal to infinity, right? Half the distance of infinity is infinity. You could also say, what's the distance from the center, which is 0, we're centered at 0 on this polynomial, to infinity, that's infinity. So that's your answer. So use that ratio test, it will work for you every time. All right, let's keep going here. So what the heck are we showing? What this means is that here's the true value of sine of x. And the power series, as n goes to infinity, is going to fit this curve perfectly everywhere. Everywhere. Which means there's never any divergence for any x value that we plug into the power series. It will equal out to the true values of sine as n goes to infinity. That's what it means. All right, so let's do one more interval of convergence problem just before we wrap it up. And we'll talk about, again, why the ratio test is the best way to go about doing this. So let's do one more. We're going to take the limit as n goes to infinity. And you can expand this out if you want to. It's not necessary, though. Limit as n goes to infinity of the absolute value of the n plus first term. That would be x plus 2 to the n plus 1 all over n plus 1 factorial. This one won't be as messy as the last one. Times the reciprocal, which would be the reciprocal of the nth term. So it'd be n factorial all over x plus 2 to the n. And that we want to be less than 1. So we solve this thing out. You have 1 more x plus 2 in the numerator than in the denominator. So that leaves you with an x plus 2. Then we have an n factorial over n plus 1 factorial. That's the same as n plus 1 times n factorial. The n factorials divide out. So now we're left with the limit as n goes to infinity. The n's can come outside the absolute value. They're going to be positive. All you have is 1 over n plus 1 from that, times the absolute value of x plus 2. That's all that's left. And that needs to be less than 1. And like in this previous problem that we did, we see that this is going to infinity. 1 over infinity is 0. So you get 0 times x plus 2. Remember that this is a finite value. So 0 is always going to be less than 1. So it doesn't matter what x value we put in. Our interval of convergence is negative infinity to infinity. And our radius of convergence is also going to be infinity. Now, is the interval of convergence always negative infinity to infinity? Is the radius of convergence always infinity? No. We're going to see in the next video how if we have endpoints that are finite, these are not, then we'll have to check them to see whether or not we're convergent there. But before we get there, a brief note. Why is it that we use the ratio test? Because it is the best inequality test that works for really any power series. It involves an inequality, it involves an absolute value, so it tests for absolute convergence, and it always works, whether your series is geometric or not. And because of that, we use the ratio test. It's all about that inequality. All right, I'll see you in the next video. Peace.